Okay, so in this lecture we will look at locks, especially in the context of POSIX threads and critical sections. So be sure to read the middle section, that is the blue section, on concurrency and threads, and then the thread API, and then this lecture is about locks, the first one, and then the next time we'll take a look at locked data structures. So remember, we want multi-threaded code. That's where we'll have a single program with multiple program counters active at any given time and multiple stack pointers that is pointing into each stack. And you'll have one set of registers for each parent and then one set for each child thread. And also remember the parent process and all the child threads share the same process address space. So why do we use all this complexity? Mainly to speed up our programs, to make it faster, to make it more responsive if you're interacting with users or other things. So there's a lot of advantages to making multi-threaded code, but if we share data, that can make multi-threading hard in the sense that you may not get the correct results if you don't take into account the fact that data is shared. So the core problem turns out to be that you can have race conditions in critical sections of code. So the fix for this is to make changes atomic, and one way to do that is to use mutual exclusion so that only one thread is able to execute its critical section at any given time. So the goal of locks is to have mutual exclusion work. So remember, threads are created by you, the developer, but then we give control to the operating system to actually schedule the threads. So we don't know what order they're going to run things in. That's one of the nice things about multi-threaded code, is that everything is going to be asynchronous. They're not going to be synchronous. And so the threaded code can have critical sections, and if they do, then you do have to worry about mutual exclusion. If your threads don't have critical sections, then great, you don't have to lock, you don't need mutual exclusion, and everything will work maybe full speed. There are programs where you can do that, where you don't have critical sections, but chances are most multi-threaded code will have critical sections. And then so to make those things work properly, you have to have mutual exclusion, and then locks are one way to implement mutual exclusion. So when you write programs, we have to use a lock in our programs, in our multi-threaded code, to make sure that critical sections are executed by just one thread and as a single atomic unit of code, roughly speaking. So we used our classic example of a critical section that was just one C language statement. So the way to use a lock is, first we have to actually identify where our critical section is. It's not always this easy that you find one statement and that's it, your critical section. You have to lock it and then everything works. In general, identifying our critical section is hard. It's not easy, but we take the easy route. We say we know, based on our analysis, that our critical section in our code is going to be this one statement. And then what we have to do is we have to instantiate a lock object. So we have to create a lock object. And so here what we've given is actually just pseudocode. This is not exactly how you do things, because of course there is a, it's, if you look at the actual declaration, it's pthread mutex t, pthread mutex type. But here we'll abbreviate that as lock type or lock t. And then you have to initialize it, and that gives you a lot of clutter in our code. To make things understandable, we use pseudocode, and we'll just say, well, here it is. Here's our declaration and instantiation of the mutex object. But of course, you guys know from the previous lecture that it's much more it's a little bit more complicated than this, but it's just one line of code. And similar thing, you saw in the previous lecture that to lock, you actually have to call this much longer method, pthread mutex lock, and then you have to pass in a pointer to the mutex, but we sort of ignore that. We just say the lock is just a lock function like this, and should have a semicolon. Okay, so this is how we'll say that we are going to instantiate a lock object, and then this is how we say that we're going to lock that lock before executing our critical section, and then we unlock it. So this is just abbreviated or sort of like pseudocode. Code will look very similar, but it's just longer and more clunky. So to make things easier, to make it fit inside a slide, we'll use this notation. Here's our instantiation of a lock object. Here's how we lock it and unlock it. And if you want to see the actual calls, just go to the previous lecture and you'll see the full function calls that you'll need to use mutexes in POSIX threads. Okay, so we'll take a long look at how exactly a lock works. And so at the base of it is the fact that a lock is a variable somewhere in the operating system, and it has to be accessed safely. So we don't really see the guts of it, but we can take a look at our POSIX threads code and see how this actual variable is defined. So let's just say for now that it's a variable and it's somewhere in the code for POSIX threads, and POSIX threads can actually use operating system mutexes and things like that, depending on the operating system. So that implementation is going to be completely dependent on which operating system you're using. So POSIX threads will work it'll work the same way, but it'll be implemented differently in Windows versus Linux. Okay, at the very core of it, you can think of it as just a variable. And that variable has two possible values. It's either unlocked, let's say 0 or something like that, and we'll also refer to it as free. The lock is free, or the lock is available or unlocked. And then the other possibility is that the lock is locked, or it's being held by a thread or a process, or it is acquired by a thread or a process. So here's the key to making a lock work, is that once you lock it, no other thread can lock it. So there are alternatives to this, but let's just say it's either locked or unlocked. So there are actually more complicated locks where you can have multiple things lock, maybe two things, but let's ignore that. Let's just say it's only got two values, and if it's locked, no other thread can lock it. If another thread attempts to lock it after it's locked, then that second thread, which is trying to lock a locked lock, has to wait. So that's the key, is it just sits there and has to wait. That is, you have one thread, it calls the lock function, and then it's able to lock. So I'm going to scroll back up. So you have to visualize two threads doing this exact same thing. So one thread creates, let's say this is a global variable and it's been created, and one thread executes the lock. It can move on and do the counter equals counter plus 1 because the mutex was not locked before this statement. Okay, so let's say one thread locks it and it's in the middle of doing this. Another thread comes by and executes similar code. It tries to lock it, the same mutex, that is this global mutex object, but it'll get stuck here. So it stays here and has to wait until the first thread does the unlock. So it's kind of hard to visualize, but you have two things going on, one thread or two threads doing this exact same code. You have to visualize one thread being able to execute this and then gets into its critical section, which is this, and while it's there but not yet unlocked it, the second thread comes along, tries to lock it, but it's stuck. So it's kind of hard, but I think by the time um, you take a look at some of these things, you'll be able to visualize it too. So you have one thread locking, getting into the critical section code, and then the other thread trying to do the same thing but has to wait. So then the first thread will do the unlock, and then as soon as it unlocks and it's done with this unlocking, the second thread can go ahead. It was stuck here, but it can go ahead and do the counter equals counter plus 1. So you're making this critical section atomic. Only one thread is able to execute this at any given time. The other threads end up trying to lock it but waiting. Okay, so these are key things. If a thread attempts to lock a locked and it's already locked, that thread has to wait, and that call to lock just does not return. It's like you're stuck there. And then as soon as some other thread unlocks that lock, then the lock will work and you return. So I know it takes a little bit of getting used to, but that's what you want to be able to visualize in your mind. So once again, once you have a lock that is locked, other threads cannot successfully lock it. They have to wait. So this implies that the lock object remembers the owner, and that's how Java works too. In Java, every single object can be a lock, and you can synchronize based on any object. And it doesn't have to be anything complicated, and Java will allow you to lock it. That's because multi-threading is built into the language. And so in Java, you have exactly this kind of situation. Every object will remember who locked that object. And then if other threads attempt to lock a locked lock, they have to wait. That is, other threads call the lock function, but that function will not return until some other thread is able to call its unlock function. And Java does exactly this. A lock actually will have a queue of things waiting to lock it. That's what is built into the Java programming language right from the very beginning. It's a nice thing about Java. And so we have the same thing in C. As long as we use the POSIX thread library, we'll have all of these things that Java has too. Okay, so remember, threads are free to execute. They are created by a developer. That is, you have control over when they are created, but then you give control over to the operating system to actually do the scheduling. So you don't really know exactly what's going to happen in the future. It's kind of hard to predict. One way to sort of make sure that things are predictable is to use locks, and so that's what developers use to control execution. And you want to do that when you have a critical section, and there the key thing is that you want to have no more than one thread execute a critical section of code. Okay, so we use the name mutex in POSIX, and that really means just the same thing as a lock. So this is actually this is a real code. So now notice, remember from the last lecture that this is the type, pthread mutex type, and I'll call this variable lock. And to initialize it, we have to assign it the value initializer. And then we say we have some int rv is equal to whatever the lock function, pthread mutex lock function returns. And remember, you have to pass in a pointer to this object. And then it's a good thing to put an assertion that whatever this block returns, make sure it's equal to 0, which means no errors. If it's not equal to 0, then there was an error, so we should just stop our program. That's what this assert does. Then here's our critical section. Of course, remember that's not always this simple. It can be much more complicated. This is a nice simple critical section that we set up way back. So continue using it. So this, we lock it, then you do the critical section, and then when you're done with the critical section, you unlock. So this is locking in red, unlocking in green, and then once again you get the return value and assert that it's equal to 0, that nothing bad happened, everything, no errors, and so you can keep going. Okay, so whether you call lock or unlock, you have to pass in a pointer to the object that you're locking, and that's needed to identify the lock. So a program can have multiple locks. You can have multiple critical sections, multiple locks, multiple resources that you need to lock, and so this is the way you identify, differentiate between the different lock objects. And although there's no need to lock every thread using a single lock, you could do that. It's not the best thing to do. It's probably better, but then your program can get complicated as soon as you start using multiple locks. So you could, worst case, you could use a single lock, but then what we'll find out later is that you end up having a lot of threads waiting, because that one single lock could become the bottleneck. Stops everything else from making progress. Okay, so now we get to the crux of the problem. How do we build these locks? What kind of code actually runs in these locks? How can we build a lock so that it works and it's efficient? Turns out we need some kind of hardware support, operating system support to implement these locks. And so pthread actually uses operating system mutexes and locks internally, and uses different ones depending on whether you're running it on Linux or Windows or Mac OS X. All right.